Hello, everyone, and welcome to our fourth lecture of GPU computing. Today, we're going to take a little bit of a break from writing code, and we're going to talk about the GPU architecture. So before that, a quick overview of last time. Last time, we looked at how to create multidimensional grids, how to store and access multidimensional data, and we did three examples throughout the lecture of writing data parallel code that manipulated two-dimensional data. Our first example was converting an RGB image to a grayscale image, and we said that a straightforward parallelization approach was to assign one thread for every pixel in the image to be responsible for generating that pixel from the corresponding RGB pixel. We saw from this example that we can create two-dimensional grids. So a grid with an X and Y number of blocks, and each block itself could be a two-dimensional array of threads. And we saw how the block index and thread index and the grid dim and the block dim variables all have X, Y, and Z components that we can use. We also saw that our data, when we can't really allocate a dynamically allocated two-dimensional array and pass it to a CUDA kernel. So if we want to dynamically allocate data to multidimensional data, we actually have to lay it out as a one-dimensional array. And the convention for storing multidimensional data in one dimension in C is the row major order. This contrasts with Fortran, for example, where the convention is column major. So the convention in C is to store data in row major order. What that means is that you store all the elements of the first row, followed by all the elements of the second row, etc. We also looked at how we have to worry about boundary conditions. And since this is a multidimensional grid, when we do our boundary checks, we have to do our boundary check across multiple dimensions. So this was the RGB to gray kernel that we wrote. We saw how to use the .x and the .y variables to get a multidimensional index for the thread, and how to do a multidimensional boundary check, and also how to access a linearized multidimensional array. At our second example, which was image blur, and that was very similar. The boundary check was a little bit more complicated because the boundary check on the input was different from the boundary check on the output. So there was a little bit more complexity with this example. And then finally, we looked at matrix multiplication as our third example last time. And we said that a straightforward parallelization approach here was to assign a thread for every element in the output matrix, and that thread would sequentially loop over the corresponding row in the matrix A and the column in the matrix B. So these were the three examples that we covered last time. Any questions about multidimensional arrays or data before we continue talking about architecture today?
Yeah, I have a question. So in the first lecture, you told us that 1024 is the maximum thread per block.
Right. Yes.
It was like a 1D array. What if it was a 2D or a 3D array?
Okay, excellent question. So yes, the 1024 is not a limit on the dimension, it's a limit on the total number of threads. So if I have a multi-dimensional thread block, then the total number of threads cannot be more than 1024. So for example, I can have a 32 by 32 thread block, that would be 1024. I can't have a 1024 by 1024 thread block. So the limit is on the total number of threads, not on the dimension. There's also a limit on the dimension of a grid, but that's fairly large, and you can always look those things up.
Okay, thank you.
Yeah?
But where does the limitation come from? Just a curious question.
We'll talk about that today.
Okay, thank you.
Yeah, you're welcome. Okay. All right, great. Any other questions? All right, let's move on. So today, we're going to be talking about the GPU architecture. So to start off, a GPU consists of multiple streaming multiprocessors. Okay, we call, or for short, we just say SMs. Every streaming multiprocessor consists of multiple cores. And these are, by cores, we mean these units that can execute arithmetic operations. Okay, and the cores in the SM share some kind of control. Okay, so by control I mean the different kinds of control logic the processors usually have to execute instructions, and they also share some kind of memory. Okay, so the GPU is broken down into many SMs. Each SM has many cores, and these cores share control logic, and they also have shared memory. Okay, and then of course all the SMs have access to the same global memory. This is the same global memory that we discussed in the first lecture, where we said we copy from the CPU memory to the GPU's global memory. So this is the GPU's global memory that we copied to. So all the SMs can access this global memory, and each SM has a bunch of cores, some control logic, and some memory inside of it that it could use for various purposes. There's actually different types of memory on the SM that we will look at. As a typical example, the Volta V100 GPU, which is the GPU that is available in the servers that you are using in the course, a Volta V100 GPU has 80 SMs, and each of these SMs has 64 cores. So you have 80 SMs, each SM has 64 cores. So this is a total of 5,120 cores. Okay, so this is how many processing cores a Volta V100 GPU has. Now the question is, how do we the code that we wrote, right? So when we wrote code, we configured these grids, and these grids were divided into blocks, and these blocks were divided into threads. So the question is, how do we take these blocks and these threads and run them on a GPU? Well, the way it works is that threads are assigned to SMs at a block granularity. And what I mean by a block granularity is that every thread block is going to be assigned to an SM. All the threads in the same block will be assigned to the same SM. Now we can have multiple threads, multiple thread blocks assigned to the same SM. That's okay. So in this illustration here, each SM has 3 thread blocks assigned to it. However, we cannot have the threads inside of a thread block, some of them assigned to one SM and some of them assigned to another SM. Okay, all of them have to be assigned to the same SM. Now, these threads, when they run on these SMs, they require resources, right? So every thread requires resources. So they need things like registers. Maybe they reserve some memory. Maybe there's also some slots for some thread-specific, control data. So threads and the thread blocks, they require resources to execute. So the SM can only a limited number of threads per block at once. Okay, so hopefully this answers the question earlier about, why is there a limited number of threads in the block? Well, part of the reason is that all these threads in the block need to run on this SM, but this SM has a finite amount of hardware, so it can support a finite amount of threads at the same time. Okay, so because the SM, each SM has a limit that can support a limited number of threads at the same time. Okay, we can only have a limited number of thread blocks running on the entire GPU at once. And because we can only have a limited number of blocks running on the entire GPU at once, if we launch a grid that has more blocks than we can run simultaneously, what happens is the remaining thread blocks are going to sit there in some queue and wait for their turn. Okay, this is not an actual, it's kind of, maybe it could be closer to a counter, if you may. So there is going to be, these threads are logically going to be waiting until the thread blocks that are executing on these SMs finish their execution, so that these new thread blocks can come and start executing. Okay, so we have SMs, we have thread blocks to SMs, All the threads in the block need to be on the same SM. The SM can support multiple blocks, and a grid can have many more blocks than the number of blocks that can execute simultaneously on the entire GPU. So if we have if we have more blocks, then these blocks will wait until one block is done so that they can come and execute in its place. Any questions?
Yes, doctor, when you say the block is assigned to an SM, is it assigned, then the block itself is assigned to one core of the SM, or are the threads divided over the cores?
No, the thread block is assigned to the SM. How these threads execute on the cores is something I will talk about shortly. Okay. But for now, what you need to know is that these thread block is assigned to an SM, and what that means is that each of these threads in the thread block is going to reserve resources like registers for itself on the SM. Okay. Other questions? All right. So this brings me to an important point, which is synchronization. So these threads, because the threads in the same block are assigned to the same SM, they can collaborate in ways that threads in different blocks cannot. Okay, and this is previously you guys asked me, what is the purpose of dividing grids into blocks? Why can't we just have a grid of threads? Well, the reason is that threads in the same block can collaborate with each other in ways that threads that are in different thread blocks cannot. One of these ways is barrier synchronization. So threads in the same block can execute can call this function or execute instruction sync threads. And what sync threads does is it allows threads that are in the same block to wait for each other at a certain point in the code before they can all proceed. Okay. And barrier synchronization is common in parallel programming. We're not going to look at an example of how to use barrier synchronization today. We will look at one later. But for now, I just want you to be aware that threads in the same block can communicate with each other, and one of the ways they can communicate with each other is by waiting for each other. So if executing some kind of code, one thread they can execute this barrier. And what this barrier says is that all the threads need to arrive at this barrier before any of them can proceed. And this helps them coordinate work for each other, across each other. Okay. Another way that threads in the same block can collaborate is using some kind of shared memory. So there's this shared memory on the SM that threads in the same block can access that threads in different blocks cannot access. And this is another way of collaborating, and this is also something we will take a look at how to use later on. And there are also other ways that we will not discuss today, but we will discuss later. Okay, but the idea is that threads in the same block can collaborate, the threads in different blocks cannot. And this is the motivation for assigning threads to SMs at a block granularity. So when we assign threads in the same block to the same SM, this makes it easier for us to support collaboration between these threads efficiently. Right? When the threads in the same block are on the same SM, that means when they need to synchronize with each other, when they need to wait for each other, they don't have to communicate across SMs with each other because they're all in the same SM. So it makes that kind of collaboration between them more efficient to support. Another important, all the threads in the block are assigned to an SM simultaneously. In other words, if I have 1,024 threads in my block, I cannot assign 512 threads to so if I have 1,024 threads in my block, and there's an SM that has 512 thread slots free, I cannot assign 512 threads of my block to that SM and then wait for them to finish and then assign the next 512. The block cannot be assigned to the SM until it secures enough resources for all of its threads to execute. Okay, so if I have 1,024 blocks, that means if I find an SM with 1,024 thread slots free, I can assign my threads to that SM. If I don't, I have to wait. Okay. Now, why do you think that is? Why do you think that I cannot? I have to assign all the threads in the block to the SM at the same time.
They might be collaborating to solve a problem, like
Right,
using shared
exactly.
memory.
Right, exactly. So, and if I don't assign them all at the same time and they try to collaborate, what happens?
They'll
You get
be
an
late.
error.
Huh?
They will be late.
They will be late. What do you mean
There's
by
an
that?
error.
So, for example, if you have three processing steps and you need to communicate at the second step, if one of them is at step one when the others are at step two, then you're going to break the program.
Well, if they're synchronizing with each other, then they shouldn't. The others shouldn't go to step two before the others are done with step one. So somebody's saying deadlock. You're right. Why could there be a deadlock if I only assign some of the threads and don't assign the rest?
Says the threads that are already in the cores that are working on the cores are waiting for the ones that are not, and the ones that are not are waiting for the ones that are to run.
Right. Exactly. Exactly. So, if I'm over here and say I have my threads are 1,000, I have a block that has 1,024 threads. And then all of a sudden there's 512 thread slots that free up on this SM. If I take 512 threads and have them run on the SM, and then the remaining 512 are sitting here and waiting, what could happen is that I could end up in a situation where if these threads try to synchronize, so to try to wait for each other at a barrier, for example, what could happen is the 512 threads that are executing here would be waiting for these 512 threads to reach the barrier. But then the 512 threads that haven't been scheduled yet are waiting for the 512 threads that have been scheduled to finish executing so that they can take their place. Okay, so that is why I cannot have some threads assigned to the SM and other threads not assigned to the SM and waiting for resources to free up so that they can be assigned to them. Okay.
Professor,
Yes.
Is the assignment also parallel, or does it happen? Does it do it? Okay, this one will take this one. This one will take this one. This one will take this one.
Okay, so by assignment, what I mean is that these threads have reserved resources to execute on the SM. That doesn't mean they're actually executing.
But what I mean is when is there one unit that for the for the scheduler, if you want?
Oh, I see what you mean. Yes, so there's a hardware unit that takes care of assigning thread blocks to SMs and scheduling the threads on the SM. Okay, and obviously there's going to be parallelism in there so that you can have scalability.
Okay, thank you.
Professor?
Okay, so we see that if we don't assign all threads to the SM at the same time, then some threads may reach the barrier and others cannot execute, so the system would deadlock. Yes, somebody had a question?
Yes, couldn't the same, like, even if we load all of them on the SM, if some of them are already in the cores, is there a way we can get them out and get others in, like do multi-threading inside the GPU?
Yes. Yes, there is, and we will talk about that.
Okay.
Okay, but the idea is that in order for them to be able to run the cores, they need to reserve execution resources like registers and thread slots and other things, and for them to be able to and we need to make sure that all of them have the execution resources they need before we let any of them start executing on the cores. So that once they start executing on the cores, we can ensure that they can all eventually execute and reach a barrier if they try to synchronize. But yes, they can do things like multi-threading, and we will talk.
Okay, thank you.
Yeah, you're welcome. Another point I'd like to make is about transparent scalability. So we saw that threads in the same block can synchronize with each other. In contrast, threads in different blocks do not synchronize with each other. Okay, so threads in the same block, they can collaborate. Threads in different blocks do not collaborate with each other. And the nice thing about the CUDA programming model not allowing threads in different blocks to collaborate with each other is that this makes these blocks independent from each other. And what I mean, the blocks being independent from each other, not talking to each other, not collaborating with each other, means that these blocks can execute in any order. Okay, so it doesn't matter what order they execute these blocks in. And more importantly, these blocks can execute in parallel, or they can execute sequentially with respect to each other. Okay, so if I have, 128 thread blocks in my grid, I can execute them from 0 to 127, or I can execute them from thread 127 to block 127 to block 0. Or I can execute them in any random order that I want, and I can execute them all in parallel, or I can execute some of them and then execute the others. The order in which I execute them doesn't matter. And what the reason this is important is because it enables something called transparent scalability. And what we mean by transparent scalability is that the same code can run on different devices that have different amounts of hardware parallelism. So if I have a device that has a small number of SMs, I can execute these blocks sequentially on that device. And if I later on get a device that has more SMs, then I can take the same code and execute it on that device that has more SMs. And these blocks that we're executing sequentially on the first device will execute in parallel on the second device. Okay, so when I say the blocks execute sequentially, I don't mean that the threads within the block execute sequentially. I mean that the different blocks execute one after the other on the same time. Question?
So you have to be careful when you select which threads go into which block, depending on if you're
right, exactly. You have to be careful. So programmers should not write code that tries to synchronize across blocks. Now, CUDA doesn't give you that. So CUDA gives you sync threads, which lets you synchronize across threads in the same block. But CUDA doesn't explicitly give you some operation that lets you synchronize across threads in different blocks. Now, people could try to do that by having some kind of, by trying to have these threads access maybe the same memory and wait for each other using, spin locking and loops and things like that. But programmers should not do that. Okay. Why shouldn't programmers write code where they try to synchronize between threads across blocks?
Because it will not scale well with different machines.
It will not scale well. What could happen if given what you know about the way that thread blocks are scheduled, given what we know about that blocks can be executed in parallel or sequentially, what could happen if a programmer tries to communicate across threads in different blocks?
You don't know the order of what's executing right now.
To avoid data races?
To avoid what?
Data races. Like
data races? No, it's not about data races. Worse than that.
We're not even sure the blocks are have the access to the same SM or memory range.
Not even that. They could have access to the same global memory. What are we not sure about? So it's written up here. If I try to communicate across different blocks,
maybe it's not even running.
Different order?
Exactly. So maybe the block I'm trying to synchronize with is not even running. What would happen in that case?
We wait for it.
We would have sequential execution instead of parallelism and slower.
I mean, that hurts performance, but there's something that's even worse. Deadlock, right? So somebody answered in the chat. Deadlock again. So if I try to communicate across different thread blocks, and what happens is that the hardware, we have more blocks than we have SMs. So the hardware is going to schedule some of these blocks and is going to put other blocks and have them wait until the blocks that are scheduled are done. If I come and try and synchronize across all the blocks, well, some blocks are running, but some blocks are waiting. So what happens? The blocks that are running are waiting for the blocks that haven't started running yet to synchronize with them. but the blocks that haven't started running yet are waiting for the blocks that are running in order for them to start to finish, in order for them to start running. Is that clear? So nothing will run. Let me go back to my architecture figure, not this one. So here, if I try to communicate between the blocks that are running on these SMs and blocks that are waiting, right? If I say I want all these blocks to wait for each other at some point in the code, what's going to happen? Well, the blocks that are running are going to wait for the blocks that are down here waiting to reach the synchronization point. But then the blocks that are down here waiting are going to be waiting for these blocks that are running to finish so that they can come and start running on the SMs. Okay, so that is why, is that point clear to everyone?
But can't you solve that at a hardware level?
How would you solve hardware level? You could, but it's very expensive. But go ahead. How would you solve it at hardware level?
I'm not sure. You know, you would see that something needs something else to start running, so you put it, I guess, into cache, and you bring something else.
Okay, so what you're saying is maybe we can take this thread block and remove it, and put the thread block in its place, and then when it's done, we can bring this one back. So kind of like context switching on a CPU, right?
Yeah, I'm not sure.
So that's what we do on the CPU, right? In the CPU, we don't have this problem because threads just context switch. So when a thread is waiting for another thread, we remove that thread from the CPU and we bring in the other thread to execute. So here, why do you think that why don't we think the GPU hardware does that, right? So why do you think the GPU hardware does not want to have to remove this block and bring in another block to execute?
It's probably most expensive to take and read.
Why is it expensive? Why do you think context switching thread blocks is expensive?
Oh, because you need a lot of cache. That's why, no? No, very expensive.
Right, you need a lot of space. Why do you need a lot of space?
Because you have 5,000.
You have a lot of threads, right? So a thread running on a CPU might be using 32 registers. So when you context switch it, you have to save 32 registers somewhere in memory. A thread block running on the CPU might have 1,024 threads, and each of these 1,024 threads might be using 32 registers. Right? So how much do you have to save? You have to save around 32 kilobytes of memory to context switch this. That takes space, but worse than space, that takes time. Right? It takes time for you to have to take all this context and store it to memory so that you can bring in a new block. Okay? So it's really not scalable for you to support context switching between threads. So that is why the hardware, when a thread block sits on an SM, it executes until the thread block is done. And when the thread block is done, the new thread blocks come in and take root. And because of this restriction, we do not, programmers should not write code that tries to synchronize across blocks, because if they do, then deadlock will occur if the blocks that they're trying to synchronize between are not scheduled simultaneously. Okay, clear? Any questions about this? Okay, so now that we've seen how we schedule blocks on different SMs, let's zoom in on one SM and see how threads are scheduled on that SM. So threads are assigned to an SM, run on that SM concurrently. And what I mean by concurrently is that I don't mean that they are all running in parallel at the same time, but they run concurrently. That there's a scheduler that manages their execution and schedules some threads sometime, then other threads at times. Okay. Now, when the blocks are assigned to are scheduled on the SM, they are further divided into units called warps. And warps are the unit of scheduling on the SIM. So these thread blocks, when I come and assign these threads to execute on these cores, I schedule them in units of warps. The thread block is further broken down into warps, and these warps are the unit of scheduling on the SIM. This shows how each thread block is broken down into warps, and these warps are the unit of scheduling on the SM. So let's talk a little bit about what these warps are. So like I said, warps are the unit of scheduling in an SM, and the size of warps is device specific, but to date it has always been 32 threads. Okay, so if I take create a thread block that is 1024 threads, these 1024 threads are going to be grouped into 32 warps that are 32 threads each. If my thread block has 64 threads, and these 64 threads are going to be grouped into 2 warps that have 32 threads each. Now, what's so special about these warps? Well, what's special about these warps is that threads in the same warp are scheduled together following the SIMD model. So who here knows what SIMD is?
Single instruction, multiple data.
Right, single instruction, multiple data. What does that mean?
You have different data, but you run the same instruction on them.
Right, exactly. So single instruction, multiple data means when threads are bound to each other by the SIMD model, the single instruction, multiple data model, what that means is that we one instruction for all these threads, and all these threads will execute the same instruction, but implicitly somehow these threads will all be executing that instruction on different data. So one instruction is fetched and executed by all the threads in the warp, but each of them is going to be processing different data. Okay, now what's the advantage of doing this? So what's the advantage of saying that all these 32 threads will execute the same instruction on different data? What's the advantage of SIMD?
Only one fetch instruction needs to be sent.
Right, only one fetch instruction only one instruction needs to be fetched. So what's the advantage of that?
Our instruction cache is much smaller. And
our instruction cache is much smaller. Well, I mean, even if I was executing a different instruction for each thread, most likely they'll be going through code, right? So they will have a good amount of locality. But there's something more important than saving on the memory footprint of fetching the instruction.
You save time. You save time and complexity of getting the data where it needs to go.
We would need an interconnect that's very elaborate to wire each instruction to its core or ALU.
Okay, I think you're saying interconnect, but I think you mean something else. You mean the hardware logic that you need to fetch a different instruction for each thread, right?
I meant interconnect, but yeah.
So is it because
it's wrong? So
the warp will finish once, and all the threads in the warp will finish at the same time?
I mean that's the result of the warp having SIMD. But the benefit of it is that, and somebody wrote in the chat, you're absolutely right, we decode it once, right? So remember, when there's fetching an instruction, it's not just about the memory footprint of fetching, but when we fetch an instruction, we have to decode it, right? And decoding that instruction requires some kind of controller that is looking at the fields of the instruction, figuring out what this instruction is, and telling the different units what to do with this instruction, right? So if I have a separate instruction decode for every single one of these 1024 threads, I'm going to need a lot of control logic. But the advantage of executing the same instruction across many different threads is that I only need one unit for fetching and executing these instructions, and I amortize the cost of that unit across multiple threads. So this is the advantage of SIMD. This is why people use SIMD. So the advantage of SIMD is that we share the same instruction fetch / dispatch unit across multiple execution units, or core, which are cores in this case. And what this does is that it amortizes the cost of control. It amortizes the cost of the control units across more execution units. Okay, so someone is asking, what if there is a branch? And that is an excellent question, and we'll talk about that. Okay, and that is the disadvantage of SIMD. But before I talk about the disadvantages of SIMD, let me first demonstrate this advantage of SIMD. So far I've been drawing these cartoon SMs with these cartoon cores, and I wanted to show you, a more complex picture of what an SM looks like. So this is from the white paper on the Tesla V100 GPU, which was released in 2017. Of course, there are newer GPUs now, but I'm using the V100 because that's the one you're working on in the assignments. So this is an example. This is the SM. This is the architecture of one SM in the V100 GPU. We said that the V100 has 80 SMs. Okay, so the V100 has 80 of these SMs. The SM itself has 64 FP32 cores. So it has 64 cores. When I'm talking about these cores, I'm referring to the floating point cores, because a lot of times what we care about is the floating point operation. So it has 64 floating FP32 cores. It also has 64 integer cores, 32-bit integer cores. But these 64 cores are actually organized into 4 processing blocks. Okay, so here you'll see that you have these FP32 cores. You also have these integer cores. You also have these FP64 cores. We have things called tensor cores, which we'll talk about much later in the course. Okay, but these 64 cores are organized into 4 processing blocks, where each processing block has 16 cores. Each of these processing block in the SM has 16 cores, and each of these 16 cores, right, in addition to the 16 16 integer cores and the tensor cores and all of these share one instruction dispatch unit and one register file. Okay, and what that is that this dispatch unit is going to fetch one instruction and execute it on all 16 of these cores. Now, obviously, a thread, a warp is more than that. A warp is 32 threads. So these 32 threads are going to be taking turns on these 16 cores. Okay, so a warp is going to be executed by one of these processing blocks, and the processing block has one dispatch unit that's shared across all 16 cores in the processing block. Okay, so this is in more detail what the architecture of an SM looks like. And by the way, this varies across architectures. So for example, the Pascal architecture also had 64 cores per SM, but those 64 cores were divided into 2 processing blocks, and each processing block had 32 cores. So different architectures have different configurations. This is the configuration of the Volta architecture. So somebody's asking, what is the difference between float and integer cores? Well, float cores execute the floating point operations, and integer cores execute the integer operations. Okay, so if you remember from 255, we said how we have in the CPU, there's the integer pipeline, and then there's also this floating point coprocessor. Well, you can think of these integer cores as containing the ALUs that do integer operations, and the floating point cores containing the ALUs that do the floating point operation.
Doctor, I have a question. If we said that one warp is executed by each processing block, and can you get like multiple warps running on the same block, on the same core?
Yes, and you actually should do that, and I'll talk about that later. But yes, so I said a warp is executed by one processing block. I don't mean only one warp is executed by one processing block. So where each processing block is going to execute multiple warps. Okay, but the warp is not, what I mean by this is that one warp is not going to execute on multiple different processing blocks. The warp is going to be fetched. We're going to fetch one instruction for that warp and execute it for all threads in that warp.
Okay, and that's why you have the L0 instruction cache for each core, right?
Yes, exactly. So there's as you observe, there's an L0 instruction cache. So each of these processing blocks has its own instruction cache. They all share an L1 instruction cache. They also all share a data cache and shared memory, which we'll look at later on. They also share texture memory, which we'll also look at later on.
Okay, and is issue
here you have this warp scheduler, and this warp scheduler is actually responsible for selecting, because as we were saying since we opened this topic, because we can have multiple warps running on the same processing block, the warp scheduler will be responsible for selecting which warp to execute at any point in time.
Can they execute out of order, and are they dispatched in order, or like what's the specific?
No, these are in order pipelines, not out of order. So remember, out of order, we said, the first lecture, that out of order execution, this is to optimize for latency. But these GPUs, they're optimized for throughput at the expense of latency. And what that means is we don't want to invest hardware into out of order execution. We prefer to take and invest it into adding more cores. So these are all in order cores.
Okay, but what if we get like different warps that, for example, if floating point 32, floating point 32, then we get integer. If all the floating point 32 execution units are busy, we will be doing nothing while we can do the integer operations. But I guess
I see what you mean. So you're talking about taking interleaving instructions from different warps. And yeah. I will talk about that. Yeah, but within a warp, the instructions are going to execute in an in-order manner. These are in-order pipelines, not out-of-order pipelines.
Professor, what's the difference between L1 and L0? Is it the same thing, just closer to the core?
L0 is private to each of these processing blocks. L1 is shared across them.
Okay, but same technology.
Yeah. This is all SRAM.
Okay, thank you.
Okay. Other questions? Okay, so we saw the advantage of SIMT, that we can amortize the cost of the dispatch unit across many cores so that we can invest more hardware to perform actual operations and less hardware in control logic. So that's the advantage of SIMT. What's the disadvantage of SIMT? Somebody had already mentioned it.
The branches?
Right, exactly, branches. So the disadvantage of SIMT is different threads may take different paths, and this results in something called control divergence. So we said that we're going to fetch one instruction and execute the same instruction on all the threads in the same warp. But what happens if different threads in the warp want to take different execution paths? What happens if I reach an if statement and some threads in the warp want to go to the then part and some threads in the warp want to go to the else part? So in this case, we have something called control divergence, when different threads want to take different control paths. And what the warp does in this situation is it has to do a pass over each unique execution path. And when it does these passes, all the instructions have to stay together. What that means is that in each pass, the threads taking the path that will execute and the others are disabled. So when I take the then, for example, if I reach an if-else statement and some threads take the true branch and some threads take the false branch, what happens is all the threads are going to go together to the true branch, but only some of them will execute, and then they will all go together to the false branch, and only the others will execute. And what that means is that at some point during this divergence, only some threads will be active while others will be inactive. And percentage of threads or cores that are going to be active or enabled during SIMD execution, this is something called SIMD efficiency. SIMD efficiency is the percentage of my cores that I am actually utilizing because there are some cores that I may not utilize due to control divergence. Let me do an example to make this. So let's say I have threads that take different branches of a conditional. So if I have code like this, where I have if threadindex.x is less than 24, then execute code A, else execute code B. And then after the if statement, I execute code C. Okay, so if I am the first warp in the block, and that refers to threads 0 to 31. What's going to happen in this case, threads 0 to 23 want to execute A, whereas threads 24 to 31 want to execute B. Okay, however, these threads are bound to each other. They all execute the same instruction. So I can't have some of them go execute one instruction and the others go execute another instruction. So what happens in this case is that at the beginning, all the threads execute the same condition. But then later on, what I'm going to do is I'm first going to go to A. Some threads will execute A, the ones that were for whom the condition was true, and the ones for whom the condition was false will be inactive. And then I'm going to do a pass through B. And then in this case, the other threads are going to execute B, while the remaining threads are going to be inactive. And remember that when I execute this instruction for all threads, that means that these cores are reserved for those threads. So these threads that are inactive are actually reserving these cores, but they're not doing anything. Okay, so I can't use the cores for anything else because all the cores execute the same instruction. So all these cores, they're either execute the same instruction or they'll do nothing. So then this is what happens in this case. And then finally, these threads will then reconverge and all of them will execute C together. So obviously there's an inefficiency here because I have these cores that are wasted because of these inactive threads. Okay, I can't do anything else with these cores because these cores are bound to the cores that are executing these other threads by the same instruction dispatch unit. Is this clear to everyone? Questions?
Yes.
Are there techniques to improve, like compiling techniques to improve the warp dispatching or scheduling in order to minimize those inactive times?
So so these are not inactive times. I mean, these are executing at the same time as this. So there's not much the compiler can do. A lot of times this divergence is dependent on the code that the programmer provides you. So if you want to minimize this control divergence, what you want to do is you want to somehow rearrange your threads so that so that all the threads that are in the same warp take the same path. But usually this is something that the programmer is able to do. It is difficult for the compiler to detect this and transform your code to minimize this divergence. That said, there is research on, some people have proposed maybe compiler optimizations where they try to minimize the divergence that is there in the code. But I don't think, I'm not sure, but I don't think that the NVIDIA compiler actually adopts any optimizations where they rearrange the threads in order to minimize divergence.
So basically the worst thing you can do is else if, else if, else if, else if.
Yes, because if I have else if, else if, else if, I'm a lot of different divergent paths. Okay, another example is maybe this is possibly even worse than the else if, is loops. So threads that execute a different number of loop iterations. So for example, I could have code like this: n equals a of thread.x, and then I execute a loop for I equals 0, I less than n plus I. And then I execute some code a. So in this case, the value of n depends on the thread index. And what that means is that different threads may have different values of n. And what that means is that different threads may execute a different number of loop iterations. But because these threads are bound to each other by SIMT, I cannot have the threads that finish the loop keep going and the threads that haven't finished the loop stay and execute the loop. They all have to wait for each other to finish the loop. So in this case, if I have threads 0 to 31 in the same warp, and if each of these threads has a different value of n, some of them might be 8, some of them 6, some of them 7, some of them 4. So here the smallest value of 4, so the first 4 iterations, all of them are going to execute, are going to be active. But then once I get to iteration 5, this thread over here is going to drop out. And then when I get to iteration 6, these other threads are going to drop out. However, they can't go and do something else, right? They're bound by these other threads because of SIMT. and then later on, some more threads drop out, and then finally some more threads drop out. And then if the largest iteration is 8, then once I'm done with all 8 iterations, then all threads can continue together. And this can really hurt you if you're not careful. If you have some kind of code where, if you have some kind of application where one of these threads executes thousands of iterations and all the other threads are executing like 5 or 6 iterations, then that one thread that's executing thousands of iterations is going to hold all the other threads hostage. All these other threads are going to sit there and they're going to be waiting for that one thread to finish executing its iteration.
Professor, in that case, shouldn't there be a way for maybe the compiler or the dispatcher to split blocks, like allow tinkering with the blocks and have all those with block index 1 to be together and so on? Like there's going to be a lot of differences between the actual instruction.
But here, the loop bound is data dependent. The compiler has no idea what this A is going, what this value N is going to be.
Okay, I misread it. Yeah, thank you.
Okay. Now, but the programmer can do things about this, and we will look later on in the course about all kinds of optimizations we can do to minimize control divergence. So now we're not going to talk about the optimizations. We're just talking about the problems. But we will talk about optimizations later. One optimization that the programmer can do is, if somehow it is possible to sort A, if our computation allows us to somehow sort A, then what we could do is we can sort A such that threads, some warps will have large values of A, of N, and some warps, the threads in some warps will all have small values of N. So this helps a little bit reduce the control divergence, and this is something that is commonly done in applications that suffer with this kind of code, and we will look at an example of this kind of optimization much later in the course.
Professor?
Yes.
I understood the problem, but aren't they going to sync later on anyway? Well, what
so they need to reconverge later. So basically, at the end of this loop, they all reconverge and continue executing together. But
I mean later on.
Okay, what about later on?
They'd have to wait for each other to finish, right?
Okay, so there's a difference between threads in the same block executing sync threads to wait for each other, and threads in the same warp being forced to stay together. So here, threads in the same warp are forced to stay together, and the reason they're forced to stay together is because they don't have the independence of executing different instructions. Okay, they must all execute the same instruction. So if one thread is done with the loop, but the others are still executing, this thread cannot go and execute different code, because all these threads they have to execute the same instruction at any point in time. So a thread can either execute the instruction that all the other threads are executing, or it can be inactive. Is that clear?
Yes, it is. But I was thinking that all these warps would be in the same block later on.
So the different can go and execute different code. So basically over here, if I'm going to have multiple warps executing this code, if one warp finishes this code, that warp can continue. It doesn't have to wait for the other warps. And later on, if I have a sync threads, then that's where all the warps in the block will wait for each other. So yes, multiple warps, one warp can keep going, whereas the other warp stays here, that's fine. But for threads in the same warp, they all have to stay together. Does that answer your question?
Yes. So the syncing would be with all the warps later on, if there is
yes,
exactly. Syncing.
Exactly.
Okay. Thank you.
Okay. Other questions about control divergence? Okay. So another topic that's related to warps and scheduling is latency hiding. So when a warp needs to wait for a high latency operation, another warp that is ready, selected and scheduled for execution. Okay, so for example, if I have this SM back to my cartoon SM. And if this SM has these different warps scheduled on the SM, okay, now obviously SM has multiple processing blocks. Each block can have a set of warps. Warps are 32 threads, not 4 threads. So this diagram is here just for simplicity. Okay, so here if I have multiple warps scheduled on the SM, these cores are going to be executing threads from one of these warps. So let's say this first warp gets executed and executes, it goes on for a few cycles, and then later it encounters a long latency operation. So this could be it loaded data from memory. It did not find that data in the cache, so it had to wait for the next level cache or for DRAM to serve that data. So in this case, the warp cannot continue executing instructions. That warp needs to sit there and wait for the previous instruction to finish. This could also be something like maybe the thread executed some arithmetic operation that takes many cycles to complete. Maybe it's executing some kind of multiplication or some floating point operation, and it takes multiple cycles to finish this operation. And the next instruction depends on this previous instruction. So the thread sit there and stall. The warp has to sit there and stall until the previous instruction is done. So in this case, I don't want my warp, when it encounters a long latency operation, like a complex arithmetic operation or a memory access, I don't want it to sit there and wait inside of my pipeline until this operation finishes. So what I'm going to do is I'm going to, once this warp reaches a point where it doesn't have a next instruction to execute, I'm going to remove it from the cores, and I'm going to bring in some other warp that's ready to execute, and I'm going to execute that warp. So in this case, I take out this warp, and I bring in this warp. And I'll keep executing this warp until maybe this warp encounters a long latency operation. And when that happens, I'm going to take out this warp. I'm going to go and find if another warp is ready. Maybe this warp is ready, and so I bring in this other warp. And then maybe this warp finds a long latency operation, so I'm going to remove this warp. And by this time, it's possible that this first warp that was executing has finished its long latency operation. So maybe the memory has arrived, right? Or maybe the long arithmetic operation has finished executing, so I can bring back this warp, and I execute this warp, and then I find a long latency operation. I remove this warp. Maybe this third warp is ready. Maybe this middle warp is not ready yet, but this one is ready, so I can bring this one back, and so on. Okay. So those of you who are familiar with multi-threading on CPU are probably recognize what's going on here. This is exactly multi-threading. Okay, but it's happening at the warp level. Okay, so what we're doing here is we're multi-threading these warps, so that we don't have any stalls in our pipeline. The minute a warp needs to stall, rather than letting it stall in the pipeline, we remove it and we bring in another warp that is ready. And by doing this, we make sure that our pipeline is always doing something. It's always busy with work. Okay?
Professor?
Doctor?
There's
Yes.
one question. Generally, if you want to have a high throughput processor, don't you want to optimize all operations to be one clock cycle exactly?
Absolutely not. That is if you want to have a low latency processor. So if you want your processor to have low latency, you optimize how long operations take. But if you want your processor to have high throughput, then what you do is you have a lot of cores, even though these cores have longer latency, and you tolerate that latency, or you hide that latency by having many threads executing together.
Okay, thank you.
Doctor, but doesn't this also involve what did you call it? Not task migration. Similar to task migration when you context switch. Doesn't it also involve context switch?
So we're multi-threading here. We're not context switching. So when I was referring to context switching, what I meant is removing blocks or threads from the SMs, saving their context to memory, and then bringing in other blocks. We're not doing this. All these threads that are executing, all these threads that are assigned to the SM, they all have registers reserved for them, and they all have memory reserved for them. Okay, but they don't all have, but they don't all execute on the cores at the same time. Okay, in other words, that brings me to my next point. In order for us over here, in order for this to work, in order for this multi-threading to work, for me to make sure that I use every single in my pipeline and I don't waste any of them, it's in my best interest to have many warps scheduled on my SM than I have cores. Okay, because if I have many more warps assigned to the SM than I have cores in the SM, that this ensures that I will always find a warp that is ready to execute. Okay, if I only have 2 warps, but I execute 1 warp, it finds a long latency operation. I execute another warp, it finds a long latency operation, and then now both of them are waiting to finish their long latency operation, and I'm going to have stalls. So to maximize the probability that I will find a warp that is ready to execute when a previous warp encounters a long latency operation, I want to have many more warps than I have cores. Sorry, I want to have many more warps than the number of warps that I can execute at the same time. Or in other words, I want to have many more threads assigned to the SM than the threads that I can execute at the same time. Okay, so we need many warps are needed so that there is a sufficient work available to hide long latency operation. In other words, there's a high chance of finding a warp that is ready to execute. And because of this, an SM typically supports many more threads than the number of cores that it has. Okay, so an SM has enough registers and enough memory and enough thread slots to support many more threads than the number of actual cores in the SM. And let's take a look at some numbers here. So here, if we take a look at the resources of one SM, depending on the different microarchitectures, you'll notice that here there are different kinds of resources. You know, the number of SMs, number of cores per SM, number of threads per SM, the max number of blocks per SM, max number of threads per SM. We'll talk about some of these later. For now, I want to focus on these 2 things. So here you'll notice that for all the different architectures, they usually support many more threads than they actually have cores on the SM. And if you look at the Volta V100 architecture, it can support 2,048 threads being assigned to the SM at the same time, even though it has only 64 cores. What that means is that we have 32 times more threads assigned to the SM than we have cores on the SM. And you can imagine that, you know, what this does is that when one of these warps reaches, you know, 2,048 threads is 64 warps. Okay, so when one of these warps encounters a long latency operation, I have many other warps that I can choose from to execute. Is this clear?
Yes, but isn't 32 times like 2048, 2008 a lot? Like, won't some threads starve, for example?
No, they won't starve because I mean there's a scheduler that's responsible for scheduling these threads, and obviously the scheduler is going to go and try and find which warp is ready to execute, and it'll execute it. But if there are multiple warps ready to execute, then obviously the scheduler is going to have some other kind of way to decide between the different warps that are ready that prevents warps from getting starved.
Okay.
How many threads per core can we execute?
So here the ratio of threads to cores is 32. A single core can only execute 1 thread at any point in time.
Oh,
right?
so
We're talking about the multi-threading aspect.
Because, for example, on x86, you can do two threads on the same core.
Exactly, that's an excellent observation. I'm glad you mentioned that. I was going to mention that. So when we compare this to CPUs, for example, in a CPU, when we do multi-threading, we usually have 2 threads running on the core. Here, when we're doing multi-threading, you saw that the ratio of threads to cores is 32, as opposed to, you know, when we have an 8-core CPU, we usually have 16 threads running on it, right? So the ratio of threads to cores on a CPU is 2. Here it's 32. So why do you think there's that big of a difference in the ratio?
Because of
CPU
long latency
is-
operations.
Right, a CPU is latency-oriented processor. So the CPU is designed such that we don't have a lot of pipeline stalls that we need to fill. Okay, we're doing all kinds of things like out-of-order execution. You know, multiple. We fetch. You know, we have wide issue. We have large caches. We have all these kinds of things to make sure that our operations have as low latency as possible. So we don't have that many cycles to fill when we're running on a CPU, and that is why we don't need to have many more threads than we have cores. Okay. On the other side, on the other hand, on the GPU, because we have these long latency operations, that is why we need to have many more threads than we have cores. Clear? Someone's saying that the GPU executes faster. The GPU executes faster because it has higher throughput, but it doesn't have lower latency. So for example, if I wanted to add one element in an array, the CPU is going to be able to add that one element in an array faster than the GPU. But when I want to add millions of elements, arrays of millions of elements, that is when the GPU becomes faster. Okay, so the individual operations take longer latency on the CPU, but the whole computation can finish faster because the GPU has higher throughput because it has so many more cores.
Why did they go down with the K40? You know, the V100 is newer than the K40, no?
Yes. So here, what you've noticed that there's a trend where they reduced the number of cores per SM, and what this does is that it allows you to have more SM. Okay, and it allows you to have more multi-threading on each SM so that you can hide latency. Okay, and there's probably all kinds of good reasons why NVIDIA does things that it does that their hardware experts know that we may or may not know. But you know, one intuition here is that over here you're increasing your ratio of threads to cores in order for you to be able to hide latency. Okay, so with that said, this brings me to another topic, which is occupancy. So we said that we want to have many more threads than we have cores in an SM. So here, 2048 is the maximum number of threads that I can assign to the SM. But that doesn't mean that any program I write will have a maximum of 2048 threads on the SM. And this is the topic of occupancy. So the occupancy of an SM refers to the ratio of the warps or threads that are active on the SM compared to the maximum that is allowed. Okay, and here by active I mean assigned to the SM, not the ones that are actually executed. The SM supports 2048 threads, but maybe because of how I wrote my code, my hardware will not be able to schedule more than 1024 threads, to assign more than 1024 threads on that SM. So in this case, my occupancy would be 50%. Now, in general, I would like to maximize my occupancy, right? I'd like to have the maximum, the number of threads I'd like to have scheduled to my SM is the maximum allowed, because the more threads I have on the SM, the better I am at hiding the latency, because I have more threads, more instructions, more warps to choose from. This is the common case. However, it is possible that we might have cases where having high occupancy might hurt performance. So in some cases, lower occupancy is desirable, but in the common case, I would like to maximize my occupancy. Now, how can I maximize my occupancy? Well, to maximize occupancy, I need to think about some of these other constraints. So here we've seen cores per SM, and we've seen max threads per SM. But we also have these other limitations, which are the maximum number of blocks per SM and the maximum number of threads per block. Right? There's also registers per SM. There's also shared memory per SM, etc. So how I choose my block size, okay, impacts my occupancy. So here the SM can support, for example, V100, the SM can support 2048 threads, but also it can support only 32 blocks, or up to 32 blocks. I shouldn't say only because that's quite a big number, but it can support up to 32 blocks. I can't have more than 32 blocks on my SM. Now, what does that mean? Well, take a look. V100, if my maximum threads per block is 1024. My maximum threads per SM is 2048, and my maximum blocks per SM is 32. If I select a block size of 256, so if I configure my kernel to have 256 threads per block, then in this case my occupancy is maximized, because if I have 256 threads per block, then to fully utilize the 2048 threads in the SM, I need 8 blocks. 2048 divided by 256 is 8. Okay. So with 8 blocks is less than 32 blocks. Okay. And with that, and therefore I can fully utilize my SM. I'm not limited by the number of blocks. However, if I set my number of threads per block to 32, for example, I'm allowed to do that. But let's see what happens. If I say that I want 32 threads per block, then if I have 2048 threads in the SM and I have 32 threads per block, to fully utilize the 2048 threads, I need 64 blocks. 2048 divided by 32 is 64. However, my SM can only support 32 blocks. So if I set my number of threads to 32, I cannot have 64 blocks. I can only have 32 blocks. So I'm only going to have 32 blocks times 32 threads. That's 1,024 threads. I will not fully utilize the 2048 threads in the SM. So in this case, my occupancy will be limited. I will not have full occupancy of my SM. And because I will not have full occupancy, my ability to hide latency is going to be worse. Okay. If I choose something like 768 threads per SM, in this case, I have a problem, which is that 2048 is not divisible by 768. So 2048 is going to be divided by 768 is going to be 2 blocks, and then there's going to be a remainder of 512 threads that cannot be used, because I cannot use these 512 to execute 768 blocks, 768 threads. Why? Because I need to make sure that I have enough resources for all the 768 threads before I schedule. We talked about this at the beginning, remember? So in this case, I'm going to have 512 threads not used. So here, when we pick the number of threads per block, we need to make sure that this number of threads per block is able to fully utilize the SM by making sure that my blocks per SM is not exceeded, and also by making sure that my threads per SM is divisible by my block size. So yes, this is, some of you observed, before you had asked me, how do we choose how many threads per block we want? Well, this is one of the considerations that goes into choosing that number of threads. Okay. Now, we saw that different GPUs have different numbers for these. So if you're running on a particular GPU, how do you know how many threads per SM and how many blocks per SM this GPU supports? CUDA actually gives you an interface for doing that. So there's an interface called CUDA device, CUDA get property. There's an API call called CUDA get device properties that allows you to query the device and figure out what are the different properties of the device, like how many threads per SM does it support, how many blocks per SM does it support, what is the maximum number of threads per block. Okay, and this here is example code on how to do this. I'm not going to get into it, but you're welcome to review it on your own. For example, here we can query the max threads per block, and we can query the max threads per multiprocessor. Multiprocessor means. Okay. And with that said, you can read more about what we covered today in chapter 3 of the textbook. And that's all for today. Anybody have any final questions?
Can you go back to the latency hiding slide?
Yes.
I didn't understand how do you switch شو اسمه the warps that are running if you have a long latency operation.
So there are these cores, right? And these cores are pipelined. Okay, and you know how we when you studied pipelining in a basic computer architecture class, you saw how when an instruction reached the point where the next instruction cannot execute before this instruction needs to wait to do something, we added stalls into our pipeline.
Yes.
So basically, instead of adding stalls into our pipeline, what we do here is we remove the threads and we bring in another thread where the instructions of that thread are independent of the other thread that's executed.
But what do we do with the threads that we removed? Where do we store them?
Well, I mean, the registers for that thread is still there. The program counter is there. There's a scheduler basically that says, okay, you don't have any instructions ready, so you're going to set aside your instructions. I'm going to remember what your program counter is. I'm going to bring in this other warp, okay, and then when you're ready, I'm going to come and I'm going to bring you back, and I'm going to restore your program counter so you can continue executing from where you left off.
And how is that different from context switching?
So with context switching, so here the registers for the thread that we are removing from execution, these registers are still reserved on the SM.
Okay? Okay.
But with context switching, we take these registers on the CPU, when a CPU does context switch, so when a CPU has two threads running at the same time, it has registers for both of these threads at the same time. But when you context switch a thread on a CPU, you take all its registers and you store them to memory in order to bring in another thread and restore its registers from memory.
Okay, I see.
That's the difference between multi-threading and context switching.
Okay, thank you.
Okay? Yeah, you're welcome. Any other questions?
But you mentioned at the same slide that a long latency operation might be an arithmetic operation.
Yes.
But how would removing it from the cores help
So it could be the case
to finish to execute?
So you remember these are pipelined, right? So I could have my ALU could be pipelined.
Okay.
Right. So the arithmetic instruction is still going to be executing a later stage of the pipelined ALU, while the instruction from another warp can come and use an earlier pipeline stage of the ALU.
Okay. I was thinking of the core being like really simple or basic.
Yeah. No, there's a lot of pipeline. These are very deeply pipelined cores.
Okay. Concerning my previous question about warps, إنه if I have to sync the warps آخر شيء for the blocks, would it be beneficial to try to optimize the control divergence? إذا أنا بالآخر I'm syncing all the warps in the block. I'm not getting why would it be beneficial to optimize the control divergence. إذا in the end they all are going to be synced. Well, مش دايما the warps in all the block will be synced.
So these are two separate things. So the problem with control divergence is I have a percentage of my cores when I execute that are not being utilized.
Okay, the thing is would be in the same SM I would have a lot of more than warps from different blocks.
Yeah, I could have warps from different blocks in the same SM, yes.
Okay, I get it.
I'm not sure if I answered your question.
No, I get it.
Okay, good. Other questions?
Doctor, can you repeat best the definition of occupancy? لأنه if you can go back to the slide of the examples about occupancy.
So occupancy is the ratio of warps or threads that are active on the SM to the maximum allowed. So if we go back to our previous slide, we said over here that the maximum threads allowed per SM is 2048, even though the number of cores per SM is 64. So ideally, I want to always have 2048 threads per my SM in my SM.
Yes.
But if for some reason, if I configure my block incorrectly, for example, or maybe I am forced to not be able to have 2048 threads per SM, then in this case, I will have fewer threads in the SM and I will not have full occupancy. So for example, if I set my number of threads to 32, and my maximum blocks is 32, then the maximum blocks is going to limit me to 1024 threads in my SM. So even though I can have 2048 threads in the SM, I won't have it because I'm limited by the number of blocks. I'm only going to have 1024. So in this case, my occupancy is going to be 50%. It's going to be the number of threads actually assigned to SM, which is 1024, over the total threads, the maximum threads that can possibly be assigned, which is 2040. Clear?
Okay. Yeah.
There could be, by the way, there could be other reasons why I'm limited by occupancy. So for example, if I write a kernel where every thread needs a humongous amount of registers, then I might run out of registers before I've reached 2048 threads. Okay, so if every thread needs 64 registers, for example, then the maximum I'll be able to, and I have 64K registers, then the maximum threads I'll be able to have is 1024. So I'm going to be limited by my registers before I reach the maximum number of threads. So this is another example where I won't have high occupancy. So there's a way for you to figure out how many registers your threads are using to be able to figure out whether you will reach high occupancy. And if you find out that your code is using too many registers, maybe you can rewrite your code in order for you to use fewer registers, or maybe you can pass a compiler flag that tells the compiler, or maybe some annotation that tells the compiler, hey compiler, don't use more than this many registers for this kernel. If you need more registers, do some kind of register splitting or things like
that. Okay, thank you.
Okay, other questions?
Just a small one. So, for example, an if-else statement is something that we use quite often. So, why don't they choose to do something like 2 instructions, multiple data?
So you're having some kind of, you're proposing some kind of hybrid a SIMT where you can have 2 different instructions running at the same time?
Yeah.
Okay, I'd be interested to maybe discuss offline what that would look like. But that starts going into the idea of SIMT is that you amortize the cost of an instruction dispatch over 32 different threads in the warp. So now if you want to have threads being able to do 2 instructions, then you now somehow need to have 2 different instruction dispatch units and somehow need to say which cores are going to go for which instruction dispatch unit, and it gets to get a little bit complicated.
Okay, I see.
Okay, but if you want to explore that idea, we can definitely talk about it offline.
Okay. Okay. Thank you.
All right. Well, if there are no more questions, then that is all for today, and I will see you next time. Bye, everyone.
Bye. Thank you.